The second postulate of Dalton's theory is partially correct because atoms of the same element can actually have different nature, difference in at least one property, which is the mass. So different neutrons will lead to different masses or different isotopes of the same element. So for example, all these species right here have one proton, which means all of them are chemically hydrogen. However, each one of them will have a different number of neutrons, which will cause the atom of each one of them to be different in masses. And despite the fact that an isotope of a given atom does not affect the chemical nature of the element, it does affect other properties. For example, the radioactivity of uranium isotopes and its ability to be used in a fission reaction depend on the nature of the isotope. Uranium will have two isotopes. One of them is uranium-238, which is actually more than a 99% abundance in any natural sample of uranium. And another fraction of an isotope that is 235, which has significantly smaller abundance. And that isotope is actually the reactive isotope in terms of nuclear fission. And it's not going to work with that small fraction with the 238 isotope around. You have to get rid of the 238 isotope in order to be able to use this 235 isotope. And the process of getting rid of the 238 isotope is called uranium enrichment. You're actually enriching the sample by increasing the fraction of the 235 isotope in your sample. And depending on the degree of enrichment, you can achieve more and more applications. Like if you get like 3 to 4% of the 235 isotope, you will be able to conduct energy production fission reactions in reactors. But in order to actually make weapons, this is not going to happen unless you reach an enrichment higher than 90%. This is why, luckily, it's significantly difficult for people to develop nuclear weapons. How we detect the masses of different isotopes in any atomic sample, or the masses of any atom on the atomic level. This is done by an instrument called the mass spectrometer. And this is a schematic diagram right here that describes the mass spectrometer. You actually have to start your experiment by injecting your sample in form of a gas. And when it gets injected, it will get ionized in an electron beam chamber that causes the atoms to get ionized. Then it will get accelerated through a successive series of electric plates that will cause it to move faster. And when it's fast enough, it will be passed through a perpendicular magnetic field. And depending on the mass of the atom, it will get attracted to the magnetic field with a different degree. So the lighter atom will get a more curved path than a heavier atom. When you detect it, depending on the position of the detection spot, you should be able to determine the mass of each spot on the spectrum. This is a typical spectrum right here for a naturally occurring muon sample. And you can see that in this sample, this instrument is able to differentiate between 3 isotopes within 1 atomic mass unit difference from each other. And the intensity of the peak is proportional to the amount of that isotope or the fraction of that. So as we said, any naturally occurring sample of an element will be a mixture of 2 or more isotopes. And that makes the atomic weight that we measure for a given element an average for all of these isotopes. For example, the atomic weight of carbon is 12.011 AMU. That does not mean that you can find a carbon atom with the mass of 12.01 AMU. That atomic weight here is the average of masses of all the isotopes existing in the sample. For carbon, for example, the naturally occurring isotopes are 2, carbon-12, which exists in almost 99% fraction, and it has exactly 12 AMU atomic mass. Carbon-13 isotope exists in a 1.11% fraction, and it has an atomic mass of 13.0034 AMU. So the atomic weight of a carbon sample is going to be the average of the fraction coming from the carbon-12 isotope plus the fraction coming from the carbon-13 isotope. So it's going to be the mass of carbon-12 isotope times the fraction of that isotope, which is the percent represented in a fraction mode, plus the mass of the carbon-13 isotope times the fraction of carbon-13 isotope. So the carbon-12 isotope contributes with 11.87 AMU, and the carbon-13 isotope contributes with 0.144 AMU. If you add them together, you will get an average atomic weight of the sample that is 12.01 AMU. Second skill in this context is actually going backward, calculating percent abundance from average atomic weights of the element. Copper is made of 2 isotopes, 2 stable isotopes. Copper 63 has atomic mass of this value, and copper 65 has an atomic mass of this value. The average atomic weight of the natural occurring samples of copper has this value right here. You can use these 3 information to calculate the abundance of each isotope. Because as we said, your average will lie in between the 2 extremes, the mass of the smallest isotope and the mass of the largest isotope. And by comparison, the average is 63.55, which is actually a lot towards the small isotope than the heavy isotope. You should expect higher fraction of the light isotope, and we will be able to calculate the exact fraction when we set up the equation. As I said, the average atomic mass of the sample, which is given to be 63.55 AMU, equals the average of the contribution of isotope 1, which equals the fraction of isotope 1 times its mass, which is 62.93 AMU, plus the fraction of isotope 2 times the mass of isotope 2, which is 64.9278 AMU. This sample is made out of these two isotopes only, which means the sum of the fraction of isotope 1 plus fraction of isotope 2 is actually equal to 1 or 100%. So using this equation here, we can find the value of the fraction of isotope 2 based on the fraction of isotope 1 to equal 1 minus x. If we use this value here in the first equation, we will find that the average atomic mass of the sample is going to equal x times the mass of isotope 1 plus 1 minus x times the mass of isotope 2. That's an equation in one variable, so we can rearrange the equation to solve for x. We'll see that this is going to equal x times this value plus 1 times 64.9278 minus x times 64.9278. So it's going to be x times 62.93 AMU minus 64.9278 AMU, right? And then we take this number to the other side of the equation. So it's going to be 63.55 AMU minus 64.9278 AMU is going to equal x times this value right here, negative 1.38 AMU equals x times minus 2 AMU. So which means x is gonna equal negative 1.38 AMU divided by negative 2 AMU. So x is 0.6889, which is the fraction of the first or the lightest isotope, which is copper 63. And from this equation right here, we can calculate the fraction of copper 65 to equal 1 minus x, or 1 minus 0.6889, or 0.3111.